Hello, and in this one I'll be looking in a bit more detail at that simple RC circuit I introduced in the last video. This is the circuit again, and as a reminder we can define a frequency response h of omega as the ratio of the output phasor to the input phasor. And in this particular case we can just identify the circuit as a form of potential divider and write the ratio of the output to the input as the complex impedance of the capacitor divided by the total complex impedance in the circuit. Simplify that by multiplying up by j omega c, and we get this expression. And that is our frequency response. Now, to get the amplitude response and the phase response, I'll need to determine what the magnitude of this function is and what the phase of this function is. And that means converting this function into its polar representation. I'll start off that by looking at where this term on the denominator would be, where 1 plus j omega rc would be on an Argand diagram. And it would be about there. The real part is 1. The imaginary part is omega rc. So if I was to complete this right-angled triangle, the magnitude of this is the length of the hypotenuse. So a good old Pythagoras would just tell me that the magnitude of this is the square root of 1 plus omega squared r squared c squared times e to the j, and the phase angle of this is this angle here, and that angle is the arctangent of omega rc over 1, or just the arctangent of omega rc. I'll write that as a tan omega rc. Okay, so I've got that expression now in terms of a complex number in polar representation, but I need 1 over this number. Well, that's just going to be 1 over 1 plus omega squared r squared c squared times 1 over e to the power of j a tan omega rc, but 1 over x to the power of a is just x to the power of minus a. Therefore this would be e to the power of j times minus a tan omega rc. Right, so I've now got my frequency response, h of omega, in the form of a magnitude and a phase term. And this is my amplitude response, and this is my phase response. If I was splitting up my total frequency response in terms of an amplitude response and a phase response, I would get that my amplitude response is 1 over the square root of 1 plus omega squared r squared c squared, and the phase response is just minus the arctangent of omega rc. And this would tell me the amplitude gain, the magnitude of the output divided by the magnitude of the input as a function of frequency. And this tells me the phase change, the difference between the output phase and the input phase, again as a function of frequency. If I were to plot this amplitude response on a graph of dBs on the y-axis and the logarithm of the frequency on the x-axis, I would get a plot like this. Now I've just mentioned a couple of points on the x-axis here. The 10 dB bandwidth, that's the frequency at which the amplitude has dropped by 10 dB. There's also a 3 dB bandwidth, which is the frequency where the amplitude has dropped by 3 dB. And it's this 3 dB bandwidth that tends to be the most common and most useful. In general, the bandwidth of a circuit is the range of frequencies for which the gain is within x dBs of its maximum gain. So a 3 dB bandwidth would be the range of frequencies for which the gain is within 3 dBs of its maximum. In the case of this circuit, where the maximum gain happens at DC, very low frequencies, that just means it's the frequency at which the amplitude gain has dropped by 3 dB. The 10 dB bandwidth is the frequency at which the gain has dropped by 10 dB from its maximum. And you may be able to see that the maximum possible amplitude gain here occurs where omega is 0, and where omega is 0, the amplitude gain would just be equal to 1. And expressing a gain of 1 in logarithmic terms, 20 log 10 of 1 is just equal to 0. Next, let's consider what the limiting cases are at low frequencies and at high frequencies. We've derived this expression that the frequency response is 1 over the square root of 1 plus omega squared r squared c squared times e to the power of j minus the arctangent of omega rc. And that means that the amplitude response, which is the modulus of the frequency response, is just equal to this. We're taking the modulus, then the phase term disappears. We're only interested in how far this complex number is from the origin in the Argand diagram. And this is what we're plotting when we plot an amplitude response. Now, first of all, at very low frequencies. At very low frequencies, we can assume that omega squared r squared c squared is much, much smaller than 1. And if we can make this assumption, then we can neglect this term in comparison to this term here, and say that h of omega is going to be approximately equal to just 1 over, should be the modulus of that, the amplitude response is approximately equal to 1 over the square root of 1, which is just 1. And expressing this in terms of dBs, 20 log 10 of the modulus of the amplitude gain is just equal to 0. And that is fairly straightforward. It predicts what we see, that at low frequencies, a plot of the amplitude gain is just a horizontal line at 0 dB. What about at high frequencies? Well, at high frequencies, we can make the exact opposite assumption. We can assume that omega squared r squared c squared is going to be much, much bigger than 1. And therefore, in the term 1 plus omega squared r squared c squared, we can neglect the 1. It's going to be approximately equal to just omega squared r squared c squared. In other words, the modulus of h of omega, which is the amplitude gain, is approximately equal to 1 over omega rc, the square root of omega squared r squared c squared. Now, if I take the logarithm of both sides of this expression here, I would get, and multiply it by 20, 20 log 10 of the modulus of h of omega. That's the amplitude response in dBs, approximately equal to 20 times log to the base 10 of 1 over omega rc. Right, well, the log of 1 over x is just equal to minus the log of x. So that is approximately equal to minus 20 log 10 of, and I'm going to write the omega in terms of 2 pi times f now. This is an angular frequency. Whenever I write omega, I mean an angular frequency in radians per second. But if I change this to hertz, I have to write this omega as 2 pi f. So 2 pi times f times r times c. Now, logarithm of x times y it's the logarithm of x plus the logarithm of y. So I could write this as minus 20 log 10 of f minus 20 log 10 of 2 pi RC. And I would get this. This is the amplitude gain in dBs. This is minus 20 log 10 of f, and this is a constant for the circuit, not a function of frequency. And this is in the form of the equation of a straight line. Remember the equation of a straight line? Y equals mx plus c, general form of a straight line. If I put this on the y-axis, that's my amplitude gain in dBs, and I put the logarithm of the frequency on the x-axis, then the gradient of the graph should be minus 20. That's a constant. I've got a straight line here with a gradient of minus 20. And that's the reason why we tend to plot these amplitude responses in terms of dBs on the y-axis and the log of frequency on the x-axis. It's because when you have circuits like this, we tend to get straight lines. And they are very easy to plot and easy to analyze. Final concept for this video is this idea of break frequency. Now we have these two asymptotes. At low frequencies, you can approximate the amplitude response as being equal to 1. At high frequencies, we can approximate the amplitude response as 1 over omega RC. And as we've seen, if we plot these on this graph of dBs against the log of frequency, both of these approximations result in straight lines. Well, those two straight lines meet at a certain frequency. And the frequency they meet is where the low frequency approximation gives the same value as the high frequency approximation. In other words, 1 equals 1 over omega RC. The low frequency approximation gives the same result as the high frequency approximation. And that happens at the frequency, omega, of 1 over RC. And this is known as the break or corner frequency. I've called it omega B in the slide up here. And if I rewrite the amplitude response in terms of omega B, I get this expression here. Amplitude response, which is the modulus of the frequency response, is 1 over the square root of 1 plus omega over omega B all squared. And I can write these omegas in terms of the frequency f in hertz as well. Omega will just be 2 pi f. Omega b, the break frequency, will be 2 pi times fb, the break frequency in hertz. So if I substitute in for omega over omega b, I just get 2 pi f over 2 pi fb. The 2 pi's cancel out. The ratio is just equal to the frequency in hertz divided by the break frequency in hertz. And I'll sometimes write the amplitude response in this form as well, where all the frequencies are in hertz. Tends to be easier to use in a lot of cases where the frequency that you're interested in is known in hertz. Next time we'll have a look at the phase response and at a slight variation on this circuit.